What if the stars above us weren't just pretty twinkling lights, but a giant cosmic clock? No ticking hands, just burning hearts of hydrogen, telling us when galaxies were born, when they'll fade, and how the universe itself will eventually end. And here's the twist. The tiniest stars live for trillions of years, outlasting everything else, while the massive ones burn out in a cosmic blink. Ready to read that clock? Stars as timekeepers. Stars don't all age the same way. A star's mass largely determines its lifetime, how much fuel it starts with, and how rapidly it burns it. Massive stars scorch through their fuel in a few million years. Medium stars like our Sun last around 10 billion years. But red dwarfs, the lowest mass, faintest stars, burn their fuel so slowly that their lifetimes stretch into trillions of years. In fact, red dwarfs less than 0.1 solar masses may live on the main sequence for 10 trillion years or more. Because of their fully convective interiors, they mix hydrogen all the way through and can use far more of their fuel than larger stars would. Thus, when you look at a red dwarf tonight, you might be seeing a star that hasn't even hit middle age. In fact, one that will outlive the universe as we currently know it. The flip side, a star's luminosity, how bright it is, scales steeply with mass. Lower mass means lower luminosity, slower burn, longer lifetime. So mass is destiny for stars, and the universe's star clock reflects that diversity. The time a star spends in its main sequence, the long phase fusing hydrogen into helium, depends on both how much fuel it has, its mass, and how rapidly it burns it. The white dwarf hour hand. When stars like the Sun, and somewhat lighter and heavier, exhaust their core hydrogen, they evolve off the main sequence. They expand into red giants, shed their outer layers, and leave behind dense cores, white dwarfs. These white dwarfs no longer burn fuel via nuclear fusion. Instead, they cool, slowly fading over enormous timescales. Because we can observe populations of white dwarfs of different ages and luminosities, the faintest white dwarfs act like hour marks on the clock, telling us how long that population has been cooling, and therefore how old the system is. The cooling of white dwarfs is very gradual. Some estimates suggest that it will take trillions of years for a white dwarf to cool to the point of no longer glowing visibly. This means that in our Milky Way galaxy, by observing very old white dwarfs, astronomers can set lower limits on the age of the galactic disk, or halo. And because these objects remain stable for such long periods, they become excellent markers of cosmic time. It's as though the hour hand of our star clock isn't just ticking in decades or centuries, but in billions or trillions of years. Stellar archaeology. Another method of reading the cosmic clock comes from stellar archaeology, studying ancient stars that formed early in the history of the universe. Some stars in the galactic halo are so metal-poor, that is, they contain very little heavier elements than hydrogen and helium, that they likely formed soon after the first generation of stars died. By measuring their ages via radioactive decay of elements like thorium and uranium, or by modeling their internal structure, astronomers can infer when star formation in the universe began. One such star, HE 1523-0901, has an estimated age of 13.2 billion years, nearly as old as the universe itself. These fossil stars help anchor the beginning of the cosmic clock. We know star formation must have begun sooner than their formation. Rise and fall of star formation. Zooming out beyond individual stars, there is a broader cosmic clock, the history of star formation in the universe. Astronomical surveys show that the cosmic star formation rate rose after the Big Bang, peaked about 10 to 11 billion years ago, when the universe was 3 to 4 billion years old, and since then has declined steadily. The universe is in effect past its prime starburst period. Our big galaxy factories are winding down. This means that the cosmic clock is not just about individual stars, but about the collective pace of cosmic creation and decay. Star-forming gas runs out, galaxies age, and the future becomes quieter. Two clocks that disagree. There's a twist in our cosmic timekeeping. Different clocks give slightly different times. For example, measurements of the universe's expansion rate, the Hubble constant, h0, differ depending on method. Early universe probes, e.g. from the cosmic microwave background, give one value 67 kilometers per second per megaparsec, while local measurements give a higher value 73 kilometers per second per megaparsec. That discrepancy is known as the Hubble tension. If one clock is wrong, our conversion between redshift, a measure of expansion, and cosmic time will be off, which means our star clocks could be misreading cosmic hours in minutes. One promising independent clock, gravitational wave standard sirens from merging neutron stars, which may provide a fresh measure of h0 without relying on traditional distance ladders. As these clocks converge, our cosmic timetable becomes more secure. Our sun's appointment book. What does this mean for us and our sun? The sun is about 4.6 billion years old and is expected to spend around 10 billion years on the main sequence. That means we're roughly halfway through its hydrogen-burning lifetime. In about 5 billion years, the sun will begin to expand into a red giant, possibly engulfing the inner planets and drastically altering the solar system. Later, it will shed its outer layers, form a white dwarf, and slowly cool. From the star clock perspective, we're living in the middle of the sun's shift from stable main sequence to the eventual faint embers. Earth's long-term future is tied intimately to the stellar timetable. Reading the night sky like a clock. When you look up at the night sky now, you're seeing much more than distant lights. Blue-white stars are cosmic teenagers, massive, bright, and short-lived. Yellow stars like the sun are middle-aged. Red dwarfs are the pensioners of the universe. Dim, long-lived, quietly burning far into the future. Stellar clusters provide way stations. The turn-off point in a cluster's Hertzsprung-Russell diagram tells astrophysicists how old that cluster is. White dwarfs tell ancient cooling tales. With modern tools like astroseismology, measuring starquakes, rotation studies, gyrochronology, and chemical tagging, astronomers are mastering many overlapping clocks to build a full timeline of cosmic history. What the future holds. Looking far ahead, the universe's star clock predicts a quieting cosmos. Star formation will wind down, galaxies will age and fade, and the last embers of stars will dominate. Those longest-lived red dwarfs will shine on long after all others are gone, trillions of years hence. White dwarfs will cool toward black dwarfs, though no black dwarfs exist yet since the universe is still too young. The universe may end in heat death or some other fate depending on the nature of dark energy and possible proton decay. But in every scenario, the timing is set by the same physics that govern stars: fusion, luminosity, cooling, expansion. Why this matters? Why should we care that stars tell time? Because by reading these clocks, we understand when structures formed, how galaxies evolved, when the sun will end, and what ultimate fate awaits. It gives context to our existence. Human history is minutes on a cosmic face of hours, days, years. We are the observers who learn to read the clock. And that's humbling and wonderful. The next time you gaze up, you're witnessing a ticking clock built from fire, fusion, and time itself. If this journey through space and time blew your mind even a little, don't forget to hit that like button, subscribe to the channel, and turn on the notification bell so you never miss a trip through the cosmos. Because out here, every star has a story, and we've only just begun to tell them.